Okay, this is number 5 from the 2010 AP Physics B exam, and this is an optics problem, a geometric optics problem, more specifically a prism-based problem. And we have this prism going, incident beam of light. We're going to get refraction here, then we're going to get refraction again over here. We know the index of the prism, and it does originate in air. We know the original wavelength of the red light, and a bunch of geometry here. We want to know the angle of refraction of theta 2 at the left side of the prism. So this is straight up a normal Snell's law refraction style problem. This is one of those n1 sine theta 1 equaling n2 sine theta 2 stuff. Good old ratio. We know n1, that's air. We know theta 1. We know n2. Ultimately, we're just going to find theta 2. So the sine of theta 2 will be n1 sine theta 1 over n2. And n1 is 1, and sine theta 1 we're going to toss in our calculator, so it's a sine of 40. And it's this whole top value divided by 1.65. Now let's give you a decimal value because this is going to be sine theta 2 and not theta 2. So let me quickly do that. We're going to get a decimal of 0.3895 yada yada yada. It actually rounds to 9.6. Now I'm going to inverse sine that number. Store it right in your calculator so you don't get a round error. And you're going to get 22.9. 23 degrees I'm sure is fine. That's it for A. B, now we're going to use the same prism. We want to know what could we do to cause total internal reflection at that right side of the prism. Now to do that we got to recognize a couple rules for total internal reflection. 1. It needs to originate in a more dense medium, and it needs to enter a lower dense medium. And that's why we're picking the right side of this prism, because the prism itself has a higher index than the air outside of it. 2. If we're not getting internal reflection at a certain angle, all we have to do is increase that angle until we do get reflection. Anything more than that will be total internal reflection. Anything less than that will refract. So ultimately, our first task for B is to increase theta 3. But we can't just say increase theta 3 because that's an indirect change. We need to know what can we directly do to increase theta 3. So let's think about that. We want the angle in which it's approaching that normal line to go up. And if we need theta 3 to increase, I'm going to draw that line up until I get to my medium here. I'm going to draw my normal line here. And I want to compare this angle I drew here to this angle here. And it's going to be really difficult to do that because I'm using, well, you know what, now I think about it, let me try using a thinner, more straight arrow. So that's the incident ray, right? And so I'm trying to grossly exaggerate that angle increase. We need theta 3 to go up. Now at that spot, I'm going to draw in my normal line. And I'm not using a protractor here, and I probably should. I'm going to eye this. I'm trying to show that this interior angle here needs to be smaller than my original angle. Perhaps you can see that in order to increase theta 3, this ray needs to be closer to parallel to my original normal line. So theta 2 needs to shrink. In order for theta 2 to shrink, if n1 and 2 won't change, we can look at the math here. Theta 2 and theta 1 are going to be directly related. So if theta 2 goes down, theta 1 needs to go down. So ultimately, we need theta 3 to increase. Therefore, we need theta 2 to decrease. Therefore, we need the incident angle to decrease. And that's the change that you're going to make. You're going to change the angle in which you're shining this red light on it so it's a smaller angle. That's it for B. C, incident beam is now perpendicular to the surface. So it's straight on. And we're going to take a thin film and place it there instead. So now we're dealing with thin film interference. We're really not dealing with a prism anymore. We want to know the new wavelength of the red light in the film. The easiest way to do that is if you understand the relationship to your incident wavelength and refracted wavelength and then your indices themselves. Ultimately, we get this relationship of lambda 1 over lambda 2 is going to be equal to n2 over n1. Now this relationship comes from the following two equations. C equals lambda over f, or more appropriately v equals lambda over f, and then n equals c over v. We're recognizing that, so let me change this because it's really going to be v because it's no longer traveling the speed of light in a new medium. We're recognizing in both of these that frequency is constant and the speed of light is constant, and we can derive this equation from that. I'm not going to do that. Ultimately, if I want to know the wavelength of the red light, I need to get lambda 2 by itself. So, because it's in the thin film. So lambda 2, I'm going to do some cross multiplying here, is going to be equal to n1 lambda 1 over n2. So it's going to be 1 times my original wavelength. That's the 6.65 by 10 to the negative 7 meters. We're going to divide that by our new medium, 1.38. And we're going to get 4.82 by 10 to the negative 7 meters. You do not need to convert this into nanometers. That said, often you will see wavelengths reported in nanometers, so just be ready for that. C2, we want to know the minimum thickness of the film. This is simple if you know the equation. The minimum thickness for all thin film interference can be related in a very simple equation. Thickness, T, that's thickness, not time, is equal to the wavelength inside the new medium, so this would be lambda 2, divided by 4. So really, all we got to do is take this number we just calculated and divide it by 4. We're going to get 1.2 times 10 to the negative 7 meters. That's it for this optics problem. Thank you.